Hello everyone, so we're back for Unit 3, Periodic Table, and these are the standards that we're going to be learning. So I didn't post these in the other videos, but I'm using them mostly as a reminder for me to stay on track and make sure I cover everything. But this video should not be as long as the last one. Unit 2 that we just did, the hour-long video, covered about 7 or 8 standards. So it was a pretty long video because it was just so much content. So with this one, we've got 3 videos or 3 standards. We'll be able to do it. So we're going to talk about predicting trends. We're going to compare and contrast physical and chemical properties based on their position and identify the properties of metals, nonmetals, and metalloids. So let's get going. If you do not already have a copy of the periodic table in front of you, you might want to. I highly recommend printing off a blank one that you can just write on. It's super handy that way because I'm going to be writing all over this periodic table. Now, just as a quick review, remember the periodic table is set up by the number of protons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth, from left to right, top to bottom. Okay, and remember that would be our atomic number. That is our number of protons. Remember, the proton determines the identity of the atom. Now, the periodic table is also set up into columns. So we have column 1, 2, all the way to 18. Okay, these columns help us determine the valence electrons. Things in column 1 have 1 valence electron, 2 valence electrons. These in the D sublevel we kind of skip. 3 valence electrons, 4, 5, 6, 7, and 8 valence electrons. Okay. And this is going to be super important for when we're talking about various things in our next unit. Our rows, we have 7 rows, 1, 2, 3, 4, 5, 6, 7, with these last 2 being members of rows 6 and 7 respectively. And our rows tell us the energy levels. Okay, so with this being said, let's jump into a few kind of big ideas. So one of them, which let's just get a nice color, we'll choose this orange, make it nice and thick, is there's a staircase on the periodic table that kind of goes like this, and this staircase is super important. So anything to the right of the staircase is a non-metal. Okay, and anything to the left of the staircase is a metal. Okay, so right, left. Anything that touches the staircase is a metalloid. Okay, and this is our big 3 groups. Now the exception is aluminum, so only bromine, silicon, germanium, arsenic, antimony, beryllium, polonium, and astatine are metalloids. Okay, these are the metalloids that we are aware of. Aluminum is, even though it touches staircase, acts just like a metal, which is probably familiar to you. Aluminum is very common. So we have these, and let's talk about the properties of metals, nonmetals, and metalloids. Okay, so metals are going to be shiny. They conduct electricity. They are ductile. Okay, and this means that it can be pulled into wires, which makes sense because most of the wiring in our TVs and all of our electronics in our houses and things like that are made of copper, and copper is a metal. It's malleable, meaning it can be shaped. Let's see, shiny, conduct electricity, ductile, malleable. Those are the big ones. And then a nonmetal is essentially the opposite of those. They're dull. They're not conductive. They are brittle, meaning you can't pull them into shapes. You can't shape them just because they break apart easily. Okay, and then nonmetals, or excuse me, not nonmetals, metalloids share properties with both. So this means if you had a compound that was both shiny, but it was brittle, right? That would be a metalloid. Or if you had something that conducted electricity but was dull, that would be something where it's sharing one property of metals or one property of nonmetals, or maybe it conducts electricity just not as well as most metals. Okay, that would be part of the metalloid feature. So we've talked about chemical and physical properties. Well, actually, most of those were just physical properties. Metals react with acid. That is one thing. So they do react with acid. They bubble, produce things. Non-metals are not reactive with acid. Just to make sure we talk about some chemical properties. Okay, they are metals are reactive with acid. Now let's talk about their position on the periodic table. So with this, we're going to need a blank periodic table, one without all the numbers and letters and things like that. So pause the video and go find a blank periodic table. Okay, so I got my blank periodic table, and the first thing we're going to do is we're going to number our rows and columns. So I'm going to do my columns in blue. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And I'm going to do my rows in green. 1, 2, 3, 4, 5, 6, 7. And then, let's see, we'll label these 6 and 7 as well. Okay, we're also going to put our staircase back in to this blank one. So it starts here. Let's make this a little thicker. Okay, so the staircase kind of goes like this. Okay, now we're going to look at some basic names for things. So anything in our first group is called the, oops, I don't want it to be quite so large anymore. This is called the alkali metals. Okay, now anything in the alkali metals are the most reactive metals. Okay, very, very reactive. Okay, alkali metals, if they are put in water, can explode. You can look it up on YouTube, but you put just a tiny bit of pure lithium or sodium or barium, strontium, things like that in there, anything in that first column will be highly explosive with water. Anything in our second column is called the alkaline earth metals. Okay, these are still really reactive, but not as reactive as things in column 1. Groups 3 through 12 are all part of the transition metals, okay? Because they're in the center, they do a lot of things. They've got a lot of weird rules. Now, starting in column 13, we have boron, okay? Now, because boron is in that, we call this the boron family. Okay, so that's the boron family. The next one is carbon, and so we call that the carbon family. The next one is nitrogen, and you guessed it, this is the nitrogen family. Okay, and then we have O. This is the oxygen family. And then with 17, even though fluorine is there, these are called the halogens. And the halogens are the most reactive non-metals. So out of all of the nonmetals to the right of this orange staircase, halogens are the most reactive. And then in column 18, we have our noble gases. Okay, and noble gases do not react with anything ever. It's why they call them noble, because nobility, you had the ability to say things really crazy and no one would show any facial expressions or things like that. They did not react to news. And so noble gases do not react with other things. And so anything in column 1, okay, because it has 1 valence electron, will form an ion that has a +1 charge. Anything in column 2 will form an ion with +2. Column 13 will always have a, oops, let's fix this. Anything in column 13 would have a +3 charge. Column 14, because it's equally close to both 8 and 0, could be plus or -4 depending on the situation. Column 15 is always -3, -2, -1, and then column 18 does not add or lose electrons, which is why it does not react. It doesn't need any extra electrons, nor does it want to give any of its away. It is very happy. This is called the octet rule, okay, which I believe we spoke about in our last video. The octet rule says that the most stable elements have a full octet or outer shell of electrons. So essentially, when the S block plus the P block are full, you get a stable atom. And in column 18, all of their S and all of their P block orbitals are filled with electrons. So those sublevels are full, and that makes the atoms extremely stable. The series down here, we have the lanthanide series, and we have the actinide series. Nobody really uses these very much unless you're specifically studying like radioactive isotopes, or maybe you're in the business of trying to create new atoms, in which case you'll probably be looking at some of these, but we don't deal with them very often. One thing that we mentioned is that these bottom ones are again the radioactive elements, and the other thing is I forgot to mention with the valence electrons what that actually like does with our atoms. So we're gonna kind of erase some of this so we have enough space. But one thing to make note of is your valence electrons help with our Lewis dot structures. Okay, and Lewis dot structures just really show you how their valence electrons are. So if in column 1 you have 1 valence electron, you would, for example, if I have lithium, you would draw 1 dot next to it to stand for its 1 valence electron. If you had beryllium, you would put 2 dots, one on 2 different sides. You have boron, okay, which 13 means that I have 3 valence electrons. I'll put 1, 2, 3 valence electrons. Carbon would have 4 valence electrons because it's in column 14. So 1, 2, 3, 4. Nitrogen has 5, so it'd be 1, 2, 3, 4, and then I would double up on that one side. And then oxygen has 6, so it'd be 1, 2, 3, 4, 5, 6. Fluorine has 7. 1, 2, 3, 4, 5, 6, 7. And then neon has 8. So you can see by looking at it this way that each atom is either going to want to gain or lose electrons to either get to 8 valence electrons or 0 valence electrons in their outer energy level, which is what the octet rule tells us. And lithium, because it only has 1, is closer to 0, so it would lose that 1 electron. My protons now outnumber my electrons, so I have a positive 1 charge. Whereas fluorine has 7 valence electrons. It really only needs a partner for this electron here, so it tries to find an electron that can be taken. So lithium and fluorine react very highly together because fluorine takes the electron that lithium is trying to get rid of, and they're both happier for it. Now, what we are going to talk about are the trends in the periodic table, and this will be our last thing, so a pretty short video, but trends are something that can be very tricky and need to be practiced. So if you have not done any practice with periodic trends, you need to do so. So the big thing is the atomic radius. Okay, so if you can remember the size of the atoms, you can remember all of them. So the atomic radius measures the size of an atom. Okay, now as you move down the periodic table, so let's say we have our nucleus in the center, and I start off at hydrogen. It has 1 energy level with 1 electron. But if I move down to lithium, lithium has 2 energy levels, and its outer electron only has 1, same as hydrogen. However, underneath that, you would have something with 3 energy levels because it was in row 3. And just by its nature, as you go down the periodic table, okay, the atomic radius is going to increase. You are adding your electrons. You're adding your energy levels. But as you go across the periodic table, your atomic radius is going to decrease. And you say, yeah, but I'm adding protons and electrons. Like, why is that not the case? Well, you can think about it like this. If I have 1, 2, 3 protons in the center, they're really big, and I have an energy level, I have these tiny, tiny electrons. The mass of the protons are so much greater than the mass of the electrons that they can kind of keep them in check. And even if I add more, as I add more protons, I'm still getting a much larger mass in the center as compared to the electrons on the outside. So as I go across, the effective nuclear charge, so I'll write this down, the effective nuclear charge, which essentially measures how effective or how good the protons are at holding everything together, that increases. So it pulls the electrons in closer to itself. It has more power. But as we go down the periodic table, the further and further away the electrons get from the nucleus, the less effect it's going to have on them, and so they can move a little bit further apart. Now, all other trends, okay, so all other trends are the opposite of atomic radius. So that is why it's so important to have that one, because you can just know that one and get all of the rest of them as being useful. So we have atomic radius, we have electron affinity. So electron affinity is when the energy when an electron is gained. Basically, how good is the electron at gaining and attracting electrons to itself? Now, as I go across the periodic table, my electron affinity increases. Now this is because the closer and closer you get to fluorine, the more and more electrons you already have, and so therefore the more you want. If I'm fluorine and I have 7 valence electrons, I only need one more, and so therefore I want that one really badly. However, lithium doesn't want to gain an electron, it wants to get rid of the one it already has. So it has a small electronegativity. So lithium is low, fluorine is very high in terms of as you move from left to right. And as you go down the periodic table, it decreases as well. So it's very much the opposite of atomic radius. Now, the reason why it decreases is because of a few things. One is that it's how much an atom wants an electron. And the further away those electrons are, we call this electron shielding. The further away those outside electrons are from the nucleus, the less likely the nucleus is to want to add more to it. It already has enough kids. It doesn't need more to monitor and things of that nature. Okay? Ionization energy. Okay, ionization energy is the energy required to remove an electron. Okay, now this is going to be the same general description as electron affinity. As I go across, it increases. As I go down, it decreases. Now, the reason why it goes across, if I get to fluorine, where I have 7 valence electrons, not only I really want to gain an extra electron, I want that 8th electron. So that means in order to take one of my 7 that I have away from me, you're going to have to put in a lot of effort. Whereas lithium, which only has 1 valence electron, is basically giving its electron away. It wants you to take it. So it has a very low ionization energy. And in terms of something like barium, okay, something a little bit further down the periodic table, it has the same number of valence electrons, however, they're further away. And when electrons are further away from the nucleus, the atom, the effective nuclear charge, it can't hold on to them very tightly, and so it's easier to pull an electron off. The last one is electronegativity. Okay, and with electronegativity, it measures the attraction for electrons in a covalent bond. Okay, now we haven't talked about covalent bonds yet, but they're when you are sharing electrons. So, for example, if I have 2 fluorine atoms, then they're pretty likely to be like, yeah, sure, I'll share those with you because you don't have enough electronegativity for me to just like gain it, right? Or for me to just figure out how to get it myself, steal it away from you. But I also don't want to give mine up to you in return, so we'll just share, okay? Whereas something like lithium is like, no, please, just take mine, okay? And so electronegativity, it does the same trend. It increases as you go across, and it decreases as you go down. Now please remember that all of these are opposite to the atomic radius, and while this video may not have been my best one that I've ever made, go back and check out some of the playlists from this unit, and also check out other resources after school and on tutoring. Good luck!